Okay, so this is a simplification and expansion example. So this is kind of a big circuit, and I want to do one that's big, so you don't, so you know that it really doesn't matter how big the circuit is. You do the same set of procedures. So give me a second to draw this. Okay, so we have 6 ohms, 6 ohms, 4 ohms, 2 ohms, 8 ohms, 5 ohms, 5 ohms, 4 ohms, 2 ohms, 8 ohms, and the current source is 10 amps. And we are going to solve for this voltage here, Vx, and this current here, Ix. Okay, and we're going to do it by simplification, and then we'll expand back out. Okay, so the first step when you do this is really to identify nodes, and I'm going to do that with a highlighter. So there's a node here where these 3 elements come together. There's a node here where these 3 elements come together. There's a node here where all these elements come together. There's a node here, a node here, a node here, and a node here. And then there's a big node where all of these things come together. Okay, so those are our nodes. I'm going to number them. So this is, I'm going to call this node 1. I'm going to call this node 2. I'm going to call this one node 3. I'm going to call this one node 4. I'm going to call this one node 5. I'm going to call this one node 6. This one node 7. And this one node 8. Okay, I'm going to highlight in a different color just to make a point here that this is all one node here. Okay, so it can be real tempting to label a node at this point, a node at this point, and a node down here, but they're all one node. It's kind of like, think about the wires like silly putty. We've stretched the node out to make it to make this nice boxy circuit. Okay, so now, and I'm going to move a little faster on this one. I'm going to make a bunch of simplifications at one time as appropriate. Okay, so I'm going to start making some notes here. At node 8, we've got 6 plus 4 equals 10. So we've got that in series. At node 7, we've got 2 plus 8 is equal to 10. And at node 5, or 6, let's do 6 first. At node 6, we've got 8 and 2 again. And then at node 5, we have I'm sorry, someone came in the room. My apologies. At node 5, we have 6 plus 4 is equal to 10. Okay, now remember that we're going to lose node 8 when we make the simplification. We're going to lose node 7. We're going to lose node 6. And we are going to lose node 5 when we make the simplification. Okay, so let's start with what we're not changing. Let me see. I'm going to move these up. I'm going to try to draw the circuit see if that gives us enough room. Okay, so I'm going to start with the 10 amp source because we haven't done anything to that. So here's the 10 amp source. Here's node 4. Okay. We haven't done anything to the 5 ohm resistor here and the 5 ohm resistor here. So let's draw those in next. So we'll call this node 1 here. And here is the 5 ohm resistor and the other 5 ohm resistor. And this is node 3. And this is node 2. Okay. So now, and let me label these 5 and 5. This is 10 amps. Okay. So now between node 1 here and node 2, we've got that 10 ohm resistor connected. I'm going to erase that node 1 here for a second. Let me move it down here. So I'm going to draw that here. I'm going to try to draw that better here. Okay, so there's this 10 ohm resistor. And then we're going to have the same thing on this side. Between node 1 and node 3, we're going to have this 10 ohm series combination and lose node 7. So we'll add that. 10 ohms. Okay. The 6 ohm and the 4 ohm resistors between node 2 and 4 will combine to 10. We lose node 5. And then we have the same thing down here between node 3 and node 4, where we have that 10 ohm resistor and we lose node 6. Okay, now let's talk about this. So this is just the resistor simplification. Now let's talk about the variables that we wanted to solve for, Vx and Ix. Do they still appear on the circuit? And the answer is yes, because we didn't do anything to the 5 ohm resistor where Vx is. So Vx still on the circuit. Okay, now let's look where Ix is. Ix was the current that flows through the 6 and the 4 ohm resistor. Remember, when we combine elements in series, we preserve the current information because they're in series, they see the same current. So we can still label Ix on this circuit as well. Okay, so this is our, now we're ready for the next step of this circuit, of this simplification. Okay, so now we should look for, we did series first time, now we'll do parallel. And between node 1 and node 2, remember this is all one node, and I'm going to highlight this again. Remember that this is all one node here, okay, node 1. So at node 1 and node 2, we have 10 in parallel with 5. And at 1 and 3, we have 10 in parallel with 5. Okay. So, and 5 in parallel with 10 is 15, or excuse me, 150 product, or, sorry, it's 50 over 15. So this is 3.33 ohms. Same thing here. Okay, so now we can do a simplification again. So again, we'll start by drawing the parts we haven't done anything to. 10 amps. Here, and this is node 4. And then coming off of that node 4, we've got the 10 ohm resistor. We haven't done anything to it. This is still node 4. This is node 2. Okay, and then over here to this side, we have the other 10 ohm resistor that we haven't done anything to yet. And that's node 3, 10 ohms. This is 10 amps. This is still node 1. Okay, but we've got these parallel combinations now that exist between node 1 and node 2, 3.3 ohms. And node 1 and node 3, 3.33 ohms. Now the question is, and I'm going to move one up top here. The question is, now again, Vx and Ix, do they exist on this circuit? Well, we didn't do anything to the 10 ohm resistor. We didn't do any simplification here, so certainly Ix still exists. So here's Ix. And then what about Vx? So Vx will still exist on the circuit as well, because when we combine elements in parallel, we maintain the voltage information. We preserve that. So this is still Vx. Okay, so now we can go to, we did parallel, it's now time to do series. So remember, we alternate between the two, and it should be pretty obvious at this point that we will have our 10 amp source. We will add the 2 resistors on the right side to get 13.33. We'll do that the same on the other side. Okay, this is still node 1. This is still node 4. But we lost node 2 when we made that series combination, and we lost node 3 when we made the series combination on the other side. Okay, now again, the question is, do Vx and Ix still exist on this circuit? Well, over here, we combine elements in series again. So yes, that current still exists on this circuit. So this is still Ix. As far as Vx goes, when we combine these elements in series, we lost the individual voltage information for each one of those resistors. So Vx doesn't appear on this simplified circuit. Okay, so now we will take this one more step. And this should be pretty obvious that we're going to have our single source and our 1 resistor. The 2 resistors are in parallel. So this is still node 1. This is still node 4. This is 10 amps, excuse me. And this is going to be 13.33 in parallel with 13.33. And that is equal to 6.67 ohms, product over sum. Okay, now Ix does not exist on this circuit because when we combine elements in parallel, so when we combine these two in parallel, we lose the individual current information. Okay, so this is our simplest point on the circuit. And so now the next steps are to expand back out so we can find Ix and Vx. Okay, so I'm going to switch to a different color so you can see the work as we go backwards. So we're going to start here at this, this simplified circuit, the 10 amp and the 6.67 ohm resistor. We know that this current is going to flow through the resistor in that direction, and it's going to set up a voltage drop here with that polarity, and I'm going to call this V1. Okay, and we're going to solve for V1. And V1 is going to equal 10 times 6.67, and this is going to be 66.67. Okay, now we're going to expand back a step. Okay, and we want to label V1 on this circuit here. So where does V1 go? Well, we have to look back at the original here. V1 has the positive terminal at node 1 and the negative terminal at node 4. So it really doesn't matter where we label it as long as it's across, as long as it references those nodes. So I'm going to label it here. But V1 is the voltage drop across all 3 elements in parallel. And so now that I know what V1 is, I can solve for Ix. okay? Because of the polarity of V1, the current IX flows from plus to minus, so the passive sign convention is going to hold. So we can write that IX is equal to V1 divided by 13.33, or IX is equal to 5 amps. Hang on, I'm just gonna, for some reason that math seems wrong to me. Just a second, please. Yep, that's it. Okay, so what else do we need to solve for? Well, let's take a step back and look at this circuit here, okay? So Vx is the only other thing we need to solve for. And Vx is the voltage drop across the 3.33 ohm resistor, which is a part of this resistor, this 13.33 one. So what we really need is the current flowing through this 13.33 ohm resistor, because that current is also this current, okay, which will help us solve for Vx. So I'm going to label another current. I'm going to call this I1, okay, and we can write a KCL equation here at node 1, or we can write Ohm's law. I1 is going to equal V1 over 13.33 as well, because it's over on the other side, so the current divides equally. So I1 is equal to 5 amps as well. Okay, so this was the answer we need. We're done with IX, but we're going to expand back a step and label I1 on this circuit. So I1 flows through the series combination 13.33 from node 1 to node 4. So that means that this current here is also I1. And now we can solve for Vx. Vx is equal to 3.33 times I1. So Vx is equal to 16.65, although that's kind of a rounded number. Okay. So that's it. We don't have to go back any further because this is as far as we needed to go to solve for Vx and Ix. So that is a bigger simplification and expansion problem, but we do them the same way, step by step. Identify the nodes, make series connections, then parallel connections, and you just go back and forth, and then you expand back by understanding how currents and voltage are labeled in the circuit.